Okay, good morning, everyone. How did your homework go? Any questions from the homework I've assigned? Please put your question, either say it or put it on chat. Okay. Any other questions? Good morning. Okay, 2G. All right, so we start with those, and if anybody has any questions, just put them on chat. Okay. So we need to find the antiderivative of the following: x to the power 3 divided by the square root of, the cubic root, x to the 4 plus 16 dx. Okay. All right. Ideas. What do you see? Do you see anything within this integral? Anyway, do you see like an inside function and its derivative? X4 plus 16. Exactly. If we look very carefully here, very, very carefully at this X4 plus 16, and we think a little bit, this derivative is almost there up to a constant. Constant never give us problem because the derivative of X4 plus 16 is X cubed. So we're going to go ahead and set up our U to be this inside function. We evaluate du dx, which is nothing more than the derivative. It's 4x cubed. We multiply by dx to isolate du. Okay. Now we stop and we start substituting everything in terms of u. So now we have this integral. Equal to everything in terms of u. All right. The denominator is fairly easy. That's the cubic root of x4 plus 16. Now it's the numerator that we have to take care of. We have x cubed dx. Now we look here. What's really going on? So I'm going to write it 1 times. If I look here, I need x cubed dx. So I'm going to divide by 4 both sides to isolate x cubed dx. So, oh, sorry. I didn't mean that. I meant to write cubic root of u. And the top part, x cubed dx, is 1 over 4 d. At this stage, we have a simple integral in u, nothing more, nothing less. We have to evaluate it. 1/4 is a constant. We pull it out. Now, 1 over the cubic root, it's u to the power minus 1/3. We have to get it ready to be able to evaluate it. Finally, I will get 1 over 4 times 1 over minus 1/3 plus 1, u to the minus 1/3 plus 1 plus the constancy. All right, now a little bit of math to let this look kind of nice, because it doesn't. Minus 1/3 plus 1, it's a 2/3. So it's going to give me 3/2 u to the power 2/3 plus a constancy. So what am I left with? 3 over 12, I meant 3 over 8. And the u, we have to go back to x, is x4 plus 16 plus the constancy. Okay. Any questions before we move on to the other one? Okay. Now we do O. And please, if anybody has any other questions, I'm ready to do it because before we move on. Okay, O is what? Okay. 1 over 1 over x, ln of x dx. Okay. It's not as clear as the other one, but you know, it's semi-clear. Ideas. Do you see anything? Things are connected in a way. Go ahead, I'm listening. Anybody?
Well, we know that the derivative of the natural log of x is 1 over x.
Okay, very good. Derivative of L, so because we see 1 over x, that's what he saw. And he saw the derivative of x is 1 over x. So what do you want me to do?
U could be natural log of x.
Yeah, we're gonna put u to be the natural log of x. Because there is this, that's what's happening here. This is ln, that is derivative. So we see basically a function and we see its derivative. We kind of see this. And then, you know, integration is a technique. So sometimes we try something, it doesn't work. It's not a big deal. We try something else. We have to get ready for that. Does anyone have a poor video quality? Okay, you guys answer him because I can't tell here. So you cannot see it? Are you being able to follow though? Yes or no? We can see it's just, okay, I will try to speak very clearly. So hopefully, yeah, I don't know what to do, honestly, from my part. Okay. I'll try to speak as slowly as possible. Sometimes so, okay. Out. Right. So du dx, I will try to speak slowly, is 1 over x dx. So now I'm going to try to express everything in terms of the new variable. So this will become, I'm going to rewrite it as follows. So to make very clear what I am doing. Equal. 1 over ln is the 1 over u. 1 over x dx, this piece, this is where we're picking up the du. Sorry. Okay, so this is going to give me finally ln of u plus c. I go back to my original variable. It's ln of x plus c. Are you still having trouble hearing me?
We can understand you.
Can you, everybody? Okay.
Yeah, it's pretty good.
All right. Any other questions from this? From the worksheet? It's your chance to ask me questions. Okay. All right. So before we move on to the definite integral, I want to ask you, simple questions just to make sure that you can answer simple questions. Suppose you remember indefinite integral is nothing more than the function whose derivative is what's inside. So my simple question is, what's the antiderivative of f prime of x dx? Very simple question. Don't be afraid of your answer.
Wouldn't it be f of x?
Exactly. Because By definition, what's the antiderivative of something? It's the function. When you differentiate it, you get what's inside the integral or the integrand. If you differentiate f prime, you get actually f prime because f prime equal f prime. Pure and simple. Write another simple question along those lines. If I remember, the indefinite integral is a function. It's really a function. So since it's a function, we can differentiate it. If I can differentiate this, what should I get?
Fx.
Yeah.
What? I can't hear you now.
It's fx.
F of x?
Yes.
Absolutely correct. Okay, so we get back f of x. And the reason is, by definition, what is this? By definition, that's really definition. This is in function f, such that, so the integral is a function f of x, such that when you take its derivative, you get f of x. So this is really the definition of the integral. Okay. All right. So today we are going to review the definite integral. And tomorrow it will be our last review of the 163 material, and then we start the 164. So definite integral. There'll be a little bit of notation. I'm sure you guys know that at the beginning, and then we do some, but you have to bear with me notation. So definite integral. So far we seen indefinite. Okay, indefinite is nothing more than a function whose derivative what's inside. That's what we call indefinite. Now definite integral is very different. So definite integral. So let me ask you, what's a definite integral for you guys? What pops up to your mind when you read the word definite integral?
It's pretty much just an integral that has like a defined boundary. So it would typically be like a, like a real number, like 2 or 4 pi, something like
right,
that.
but what's the definition of it? I mean, when you are computing this, which is of course you guys all know, what do you think? What does it mean?
The area under the curve from that point to the other point.
It's the area under the curve. That's very good. Anybody else? Okay, so that's the idea we are going to emphasize. And the question is, how did we get this area? I mean, what's the formula that will help me get this area? So definite integral. So the idea of area is the one I want really to talk about. So first, before I talk about definite integral, I need to talk about something called, so everything I say, you guys have seen it, but I would like to review it with you, something called the Riemann sum. Riemann sum with n subdivision. Subdivision. And you guys in calculus 1, you've seen a lot of that. You saw something called left Riemann sum, right Riemann sum. I will emphasize only one of them because it does not really matter which one you use. So we're going to talk mainly in this class about the right Riemann sum. So what's a Riemann sum with n subdivision? So we start with a function f of x. Be a function defined on an interval AB. Okay, so this is my picture. I have a function, and this is my pencil. Very good. Yeah, so this is my function. Okay, please pencil. Yep, here we are. So that's my A. And that's my point B. So these are, if you wanna, you guys call them my limit, my bounds, A and B. Now we take this interval and we divide the interval into n sub-equal intervals. So we divide AB, we divide AB into n equal subintervals, n equal subintervals. Right? So what do I mean by that? Means I'm taking this interval and we're going to divide it into n equal pieces. Equal. It's one piece. So now I'm defining the meaning of the word Riemann sum. And I'm going to call this names. I'm going to call, because a lot of them, this endpoint, I'm going to give them names. I'm going to call this endpoint x0 because we have n of them. This one I'm going to call x1. This I will call x2. I call this x3. I keep going. The last one, because I have n pieces, those are n, this would be called x sub n. And the one before it is the one before it. It means n minus 1. So if we have 8 subdivision, this would be x8. 10 subdivision, this would be here x10, and so on and so forth. Now, what's the length of every subinterval? So we're going to call delta x the length of every subinterval. So what's the delta x? The length of every subinterval. So delta x is equal to what in my problem? Anybody remember? What's the length of every one of them? Let's see, from here to here, the whole interval from here to here, it's b minus a. B, you take away a. So this length is b minus a. If I divide it into n equal pieces, each one of them is going to be b minus a over n. So that's the length of every subinterval. So I start by taking the interval AB and subdividing. Now, what's the definition of the right Riemann sum? So that's the definition. There is something called left Riemann sum, but I'm not going to do it because it actually doesn't really matter. So the right Riemann sum, or sometimes I will call it only Riemann sum, just to be to simplify, is defined as follows. We take subinterval from a to x1, and we consider the following. This is x1, we have a function. We take the value of the function at x1. So from here to here, so remember this point here, right there, this is f of x1. We take the value of the function here, and we multiply it by this little delta x. So we take this sum. So we take f of x1, the value of the function at x1, times the delta x. And we add to it. We're going to repeat the same thing. This is x2. We're going to take the value, whatever the function evaluate at this point, f of x2, times the delta x. And this is from here to here, this point to right here. This is the x2, f of x2. And we're going to take that. The value of the function at x2 times delta x plus. So the word right is coming from the fact that on every subinterval, I'm taking the value of the function at the right endpoint of the subinterval. At the right endpoint of the subinterval. And I keep repeating. Now I'm going to do that for x3 and x4 and so on and so forth. So I keep repeating. Now finally, since I'm taking on every subinterval, at some point I'm going to be here. So I'm going to take f at x and minus 1 times the delta x. And finally, I'm going to take f of x n times delta x. So I'm going to keep adding. The The last two will be f of xn minus 1 times delta x plus f of xn times delta x. This sum that you see, which is, again, value at a function at a point, delta x, value of the function times delta x, and so on and so forth. This sum is called a Riemann sum. And we call it right because on every subinterval, I use the value of the function at the right endpoint of the subinterval to compute. There is something called the left, where we use the left endpoint. Okay, so crucial sum. So when we talk about Riemann sum, that's really what we are talking about. Now, what happened? So that's with n subdivision. The idea now is the following. We can take 10 subdivision and compute the sum. Then we can take 15 subdivision and compute the sum. And we will do a little bit of that. And we're going to take 50 subdivision, 100 subdivision. What happened is the following. When the number of subdivision, when the number of subdivision, it means when n becomes very large. What do I mean by n? N is the number of subdivision. It means when delta x becomes what? Finish my sentence. It's when we take a lot of subdivision, like 100 of them. Delta x becomes what? Anybody?
0.
Not 0. Better than that. Not 0. Not 0. What do you mean by 0? It doesn't become 0. And if n is a million, is delta x 0?
I mean smaller.
Small, very small. When delta x becomes very small. Okay. So we compute those Riemann sum. It means we compute the sum. As when n becomes larger, it means when we start subdividing into more and more interval, all those sums become close to a number. So we realize that if we take 100 subdivision or 200 subdivision or a million subdivision, all the answers are actually going to be very, very close. This number that all those sums become close to is what we call the definite integral. So the definite integral is, by definition, that's the definition of definite integral, there is no other one. So by definition, the definite integral is those sum for n very, very large. So the Riemann sum become close to a number that we call definite integral. And now I'm going to define it in a more formal way that we call definite integral. And why it is area, it will be clear in a second because you guys are absolutely correct. It's an area. All right, so definite integral will be nothing more than those sums. No, nothing more when the number of subdivision is very large. So now let us write the formal definition of the definite integral. But before I do that, let us, I'm going to write Riemann sum in sigma notation. We're going to write Riemann sum in sigma notation. Okay, so this sum, I'm going to rewrite it again. So Riemann sum is, which is f of x1 delta x plus etc. f of xn delta x. Instead of writing plus dot dot dot, we know that there is a sigma notation. This will be written as sigma. What's changing here is this index. So we're going to write a sigma f. Be very careful. xi delta x. That's the notation. And my I, which represent this one here, to x1. It represents the x2, and so on. So my I goes from 1 all the way to n. So now finally, I define the definite integral for us. So definition. Definition. Okay, let f of x be a function defined on an interval a, b. So the definite integral of f from a to b denoted by, and that's the notation. The notation that you know, denoted by a wiggly number a, b, f of x dx is defined as follows. Okay, so now the definition, that's the only definition. So definite integral is actually weird because it's the definition of this sum. So the definite integral is equal to it's nothing more than those sums, those Riemann sums. So you evaluate those Riemann sum for 10 subdivision, 100 subdivision, a million subdivision. So you keep evaluating those Riemann sum, and then you start asking yourself when n becomes large, what's the number that are getting close? Now, mathematically, I cannot tell you that. Mathematically, the way we express it is by saying you compute those sums for n, and you ask yourself what happened to them. That's the idea of a limit. It means what happened to them when n goes to infinity. It means what happened to them when n becomes very large. Okay, so that's the definition of the Riemann, the definite integral. Absolutely crucial because all the first part of the course, the first application will rely on the definition because that's really what it is. Now, a word about notation. Where is this notation coming from? I mean, it's a weird notation. Where is it coming from? First, the notation is due to a mathematician and philosopher called Leibniz. He came up with this notation. And where is this notation coming from? Let us talk a little bit about it. Okay, this piece here, what does it represent? Anybody? That's the definition. The notation is trying to reflect the definition. That's really the idea. That's really where Leibniz came from. So what do you think this wiggly thing comes from? Anybody? What does it represent from here?
The submission sign, which looks like E.
The what? Repeat, I think you're right.
A summation sign, which looks like E.
It's the summation sign, but let's see why it's the summation line. It's like S, not E. S, right? So the sigma is sum, and S represents sum. It's basically took S and it's being elongated. That's really, and S, this is for the sigma part. That's exactly how he came up with the notation. So this represents a sum. F of x dx basically remind us what we are doing. It means we are adding quantities of the form f of x times delta x. So that's really where the f of x dx coming from. It tells me that I am adding f of xi delta x. A and b remind us that is the interval AB we are dividing. So that's where he really came up with this notation to reflect actually the meaning of the definite sum. So the definite integral is this number, and that's the notation for it. Okay. Before we compute some Riemann sum and estimate some integral, let us talk about the graphical interpretation. And this is where I go back to what you guys started with, that it is an area. So graphical interpretation. So that's the definition. That's just going to be the heart of it. So graphical interpretation of the definite integral. So we define the integral as a limit of those sums. So to understand the integral graphically, I have to understand what those sums represent graphically. So as you realize, I am using the definition to understand that. So what does those sums represent graphically? Okay, so I'm going to understand this. If I understand this, I understand that. All right, I'm going to break it into two cases. Case one, f of x takes positive value on AB because it's going to matter in the picture. So suppose f of x is positive. So now this is my graph. That's my function. And my function is, this is my A, this is my B, and this is my function positive. So I'm not allowing negative value. So the graph is above the x-axis. This does not go below the x-axis. All right, so that's my graph. Now, f of x is positive. I want to understand this piece. If I understand this piece, I understand that. So as you realize, I'm starting from here to here, not the other way around. So let us understand this. I'm going to divide this into pieces. I won't do a lot because it's tedious, so I'm not. And then like I'm going to call this x1, x2, x3, x4, x5, x6, and this is x7. And let me understand this Riemann sum. So I'm going to understand f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x plus, I don't want to bore you more than that, f of x7 times delta x. So let us see graphically what does it represent. So what is f of x1? This is x1. From here to here, this length is f of x1. And this is delta x, the length of this little piece. So this is delta x. This is my delta x. And this is f of x1. And this is delta x. Okay. So when I'm taking f of x1 times delta x, what am I getting graphically as far as this picture is concerned? I know you know the answer, so I need your help. So this piece, how can you interpret it graphically?
Just length times width.
Yeah, graphically in this picture, but yeah. So it represents what? Length times width is what? Anybody? Length times width of length times width of what? Of this rectangle, right? From here to here is f of x1, but that's x1, and this is delta x. So that's the length times the width of this rectangle. So what it's gonna represent is the area of this rectangle. So if I call this R1, the area of this rectangle is the first piece. So this is the area of R1. Okay. F of x2 times delta x, this is x2. I use another color for it. This is x2. F of x2 is the height from here to here. That's f of x2. I multiply it by delta x. I get the area of this rectangle. So this is represent the area of R2. So the Riemann sum, when I start interpreting it, that's really what it means. And then as you expect me to do, I'm going to take, this is x3, f of x3 is the length from here till we touch the graph. That's f of x3. And delta x is this little width. So now I'm getting the area. I'm going to call this R3. I get the area of R3. Plus, etc. So I keep adding areas. So I'm going to add the area of this one, then the area of that one, plus the area. So this is really what the Riemann sum represents when the function is positive. And finally, that's the last point, I will get the area of this one. And according to my notation, this will be R1, R2, R3, R4, R5, R6, R7. So this is R7, plus the area of R7. Okay, so I took 7 subdivisions, so I can draw the picture. So the Riemann sum in this case represent basically, so this is the sum of the area of the rectangle. And as you realize, I'm trying to understand the Riemann sum, so I understand the integral. Now what happened? As n goes to infinity, when I take more and more subdivision, and when I start taking more subdivision, so instead of taking 7, let me take 14, those rectangles will start filling up the region more and more. So as n goes to infinity, the sum of the rectangles, they become close to the area. So the sum of the area become close to the area of the region below the graph. So it means that the picture is this one. This is the function A and B. As I take more and more subdivision, this sum, the value that I get from the sum, is actually going to become close to this area under the graph. So in this case, when n becomes infinity, those sums are basically what the definite integral is. So when n becomes very large, so we get that the integral would represent the area under the graph of f. For x between a and b. Okay, so our idea now here, if f of x is a positive function, the Riemann sum will represent the sum of those areas of the rectangle. As you take more and more subdivision, those rectangles will start filling up the region under the graph. So when n becomes very, very large, the sum of those areas become actually the actual area under the graph. But by definition, the definite integral is nothing more than what happened to the sum when n is very large. So the definite integral will be the area. And that's what you guys started with. Now, case 2. What if my function is sometimes positive and sometimes negative? What will those Riemann sum represent? Therefore, what does the integral represent? Any idea? Any idea what happened when the function takes positive values sometimes and negative values sometimes?
I think when the fx gets negative values, then we will subtract the area which stays under the x-axis.
Okay, so the definite integral would represent repeat what you said.
So when the f takes negative values, the area that stays under the x-axis will be subtracted from the
absolutely
lost area.
Absolutely. And let us see why this is really happening. So f of x takes positive and negative value on AB. I'm going to show you why what my classmate is saying is absolutely correct. We're going to draw the picture and analyze carefully the Riemann sum. So this is my picture now. And I'm going to positive and negative, both values. I'm not going to allow only positive value because functions are not always positive, but we have to give meaning for the definite integral. And I'm going to divide it into, let us see, 1, 2, 3. Not very equal, but let's accept that. I don't want a lot of subdivision because I have to explain. And this is x5, x6, x7. There is no reason why I'm taking 7, but I want to take something that I can explain without a lot of being tedious. So let's analyze the Riemann sum in this case. So I'm going to analyze f of x1 times delta x plus of x2 times delta x. Because analyzing those sum help me analyze a definite integral. F of x4 plus f of x5 delta x, f of x6 delta x, and f of x7 delta x. Oh, let us analyze them carefully. All right. F of x1 times delta x. I go back to my picture. That's x1. F of x1 is from here to here. And the delta x is from here. If I call this R1, so f of x1 delta x, that's area of R1. Plus f of x2, that's the height from here to here, times delta x, that's the area of R2. So far, the function is positive, as you realize. So the part of the Riemann sum have the same geometric interpretation. Nothing is changing. F of x3 is the length from here to here. That's my delta x. So again, that's going to give me area of R3. Plus, I get this piece. F of x4, this is a 0. So by coincidence, f of x4 is 0, so that's 0. So let's not worry too much about that. Plus, that's the piece I want you to understand carefully. What does f of x5 times delta x represent? This is x5. And this is f of x5. F of x5 is negative. And this is my delta x. So when I take f of x5 times delta x, what do I get? I'm going to call this rectangle R5. What do you think I get? Let's see what the problem is. The value of the function at x5 is a negative number. It's not positive. So let me say f at x5, just for the sake of argument, since it's negative, is let us say -2. Don't write this, I'm trying to explain. So when I take f of x5 times delta x, I'm going to get -2 times delta x. But what does this really represent for me? If I factor out -2, I'm going to get -2 delta x. So what I'm going to get is 2 delta x, which is the length from here to here. That's my 2. That's the length. That's not the value. That's the length. Times delta x will give me the area of R5. So this is going to give me minus the area of R5. So this product will not be the area anymore. It will be minus the area of this piece right there. And the reason is because f of x5 is a negative number. So that's really the P. That's exactly what's happening. It's -2. Factoring out, I'm getting minus the area of R5 because 2 is the length from here to here. Minus tells me that it's below the x-axis. So this will give me minus the area of R5. So this part of the Riemann sum is giving me minus the area of R5 plus minus the area of R6 plus minus the area of R7. Now, if I do a little bit of math, I will get that this Riemann sum will give me the area of R1 plus area of R2 plus area of R3. But then I'm going to factor out this minus. Let's give me that, minus area of R5 minus the area of this plus that plus this. So what the Riemann sum will actually give me is the sum of the area of the piece above taking away the area of the pieces below. So the sum of the area of rectangle above the x-axis minus sum of area of rectangle below the x-axis. So what the Riemann sum becomes. So that's how understanding the Riemann sum is going to help me understand really what the definite integral. So when n becomes very large, the picture will become the following. This is my function right there. That's my A and that's my B. Okay. And let me call this region A1. I'll call this region A2. So when n becomes very large, those sums, which by now are the definite integral, become. For the part of the graph above the x-axis, the Riemann sum gave me the area of it. For the part below the x-axis, the Riemann sum gave me minus the area. So the integral is going to be area of region above the x-axis minus, big minus, area of region below the x-axis. And this is totally coming from the definition of the Riemann, of the definite integral, because it's a Riemann sum below the x-axis. That's really me. So in my picture, it's the area of R1 minus the area of A2. And sometimes we call this signed area. Don't worry about that word, but sometimes you will see the word signed area because it's actually the definite integral is not the area. If the function takes positive and negative value, it's the area above minus the area below. So the definite integral can be very well a negative number. And that's the idea. All right, so our analysis here, what I'm trying to do is basically to emphasize the following idea, is that the definite integral, its definition is this sum. It's the Riemann sum. So we'll go from here to here. So we take this Riemann sum for larger and larger interval, a larger subdivision. And what we get when we take the sum is really what we mean by the definite integral. And that's the heart of it. Now, what we're going to be doing in this class very soon is actually, we're going to, a lot of time go backward, means we're going to have the sum. And then from it, we're going to go to the definite integral. That's how we will do, and you will see that very soon. All right, I'm very much short of time. For tomorrow, your homework would be actually to, I'm giving you a function. Okay, I'm giving you two exercises. I'm giving you a function, and I'm asking you to compute the right sum by hand for 8 subdivisions. So please make sure you can do it. And then I'm asking you to do it to use a website to evaluate it for 10, like 100 subdivision, because I want you to see that the Riemann sum will get me, when you take more and more subdivision, you get almost the same number. All right, so you're going to have two problems where you have to compute the right Riemann sum. All right. Any questions before I let you go? Any questions? All right, did the video got better or you still had problem following? Hello? Okay, did the video got better or you guys were able to follow?
I was able to follow.
Okay, all right. Have a good day, guys. And I have office hours. If you have any questions, please make sure to stop by. I have office hours from 9 to 10. Bye-bye for now.
Bye.
Have a good day.